I'm Alex Woodfinden. I'm a second year PhD student at the Worsley Centre for Astrophysics. Today, I'm going to be talking about void galaxy measurements made in the eBOSS survey. This was work done in collaboration with Sajari Natha, my supervisor Will Percival, along with others. Let's start by talking about what we can get out of galaxy surveys. These surveys are a 3D map of a particular tracer and typically used to measure 2-point statistics. The information that we can get out of this are distance measures dm, dh, the expansion rate hz, and the growth rate of structure s sigma 8. But we can get more out of these surveys than just results from BAO and RST measurements alone. One technique with what we can do with these surveys is restrict ourselves to regions where linear theory is a better representation of reality. If we restrict ourselves to these regions, we can use just linear theory to model the behavior, and we can therefore pull out information down to smaller scales than BAO and RST results alone. The areas that we're looking to do it in this work are voids. Voids are areas where the motions of galaxies still track their primordial form, and linear theory can be better used to describe these galaxies. Let's go into exactly what voids are. Voids are just large-scale underdensities, regions of space, like you can see here, that are devoid of galaxies. In the figure I'm showing, what we're seeing is a cosmic web, and highlighted in the red circle is one example of an underdense region. You can see many others in this map. While the profiles in this region is not necessarily linear, the motion of galaxies will still track the primordial form. This means that they'll be closer to Zeldovich behavior, and therefore easy to model. So let's jump into the basic ideas of what void analysis is. What we do is we start with a tracer. So for example, LGs, ELGs, quasars. We can map out the positions of this tracer and produce a 3D map. So that is represented here by the blue dots, in this figure. From these blue dots, we can construct a density field. We can then find undensities in the field, which are shown with these orange ovals. Once we have identified these underdense regions, i.e. voids, we can take these voids and stack them together. Voids will have a random orientation and shape. That's because they have no preferred direction, so they'll just be randomly oriented. If we take enough voids and stack them on top of one another, we will come away with a spherically averaged object, as shown here. So you take the voids and you just keep stacking more and more voids until you get an object that will be spherical on average. The average void profile can then be used to measure the Alcock-Paczyński parameter. The Alcock-Paczyński parameter measures the Alcock-Paczyński effect, which is where the diameter of an object along a line of sight will become distorted with respect to the diameter perpendicular to a line of sight if the wrong cosmological model is used to convert redshift into distances. We can use the ratio of the diameter perpendicular to the line of sight to the diameter along the line of sight, and use that ratio to get a measure of the Alcock-Paczyński parameter, FAP, shown here. The way that we actually measure void profiles and distortions is by using void galaxy cross correlations. Here, we take our void centers that we have found in our tracer fields. The void centers are shown here as the red dots in our tracer field represented by the blue dots. We can correlate these center positions with nearby galaxies. Here, these concentric circles out from the void centers show the bins in which we count galaxies. We can count the galaxies in these bins and determine the density of galaxies. We can then use a random field, and we can do the same thing, and we can count out how many objects we expect to find in a random field. We can use the probability as a function of radius of finding a galaxy in our voids compared to that of a random distribution, and we can get our correlation function. Here the rings are showing these bins that we're counting galaxies in. In the center of these voids, we expect to see no or very few galaxies, and therefore the correlation function will have a value close to -1, meaning that there are no galaxies in that area. If we look far out from voids, we're no longer measuring this object, we're just measuring galaxies in the matter field around voids. And so we expect to see no more or no less galaxies than we would expect to be as we would expect to see in a random field. What that means, its correlation function in these areas will equal 0. In order to perform the void analysis, we use the compression of correlation function into Legendre multipoles. Here you can see the monopole and quadrupole of our void galaxy correlation functions. Looking at the shape of these functions, you can see some clear zones. In the center, you have very few to no galaxies, so the monopole is close to -1. As there are no galaxies, there will be no distortions to the correlation function, and therefore the quadrupole will be 0 as there is no distortion. The next region we see is zone 2. In zone 2, you'll have an underdensity that has been stretched along the line of sight, as these are measuring galaxies that will be flowing away from void centers. As they are flowing away, and we have this underdensity being stretched, we will see a negative quadrupole. The third zone that you see when you look further out is when you reach the void walls. So as you're measuring in the void and you expect less galaxies, at some point you will hit the edge of a void. As we are measuring the edge of the void, the edge must have some matter in it, and therefore we expect to see more galaxies than in a random field. This is why the monopole goes above 0 in this case, as we are more likely to find galaxies versus some average random field. Due to the Kaiser effect, the effect of Kaiser squashing in an overdense region, in this zone we will have a quadrupole that is greater than 0. The last zone that we have is when you go much further out from a void and you're no longer in a void. In this area, you expect to find a galaxy at the same probability as you expect to see in a random field, as you're no longer looking in a void, and therefore the monopole will go to 0 as you're finding as many galaxies as you are seeing in a random field, and the quadrupole will go to 0 as the motions of the galaxies will be random and there'll be no large-scale squashing or stretching of these galaxies. So as I mentioned, the warping of the quadrupole is caused by two main effects. First, we have redshift-space distortions. This is where the peculiar motions of galaxies produces an additional velocity component along the line of sight. This will elongate underdensities and squish overdensities when converting from redshift to distances. The warping from these redshift-space distortions are proportional to the growth rate. The second effect that I've mentioned previously is the Alcock-Paczyński effect. These are distortions introduced by transforming redshifts into distances using the wrong cosmological model. We can account for this in the usual way by adding alpha parameters in the perpendicular and peculiar distances. We can then rewrite the correlation function with the addition of these alpha parameters, as is shown in the bottom line here. Both of these effects will distort the quadrupole in distinct ways. Here is shown there are two different effects on the quadrupole. The left is the effect of changing the growth rate at a fixed cosmology, and the right shows changing of the ratios alpha perpendicular over alpha parallel with all else fixed, i.e. the left is showing the effect of redshift-space distortions, and the right was showing the distortions from the Alcock-Paczyński effect. As you can see, these two competing effects lead to two different distortions in the quadrupole. What this means is we can now accurately use joint fits to model these two effects and pull up values of the growth rate and Alcock-Paczyński parameter. So that's enough background for now. Let's talk about a recent paper where we applied this technique to the eBOSS sample. The eBOSS survey is a galaxy sample in the redshift range 0.6 to 1.0. The sample that we used combined the high redshift tail of the CMASS survey with the additional galaxies from the eBOSS survey. The figure from the top right shows this. In blue, we have the high Z tail of CMASS galaxies, which go from redshift 0.6 up to roughly redshift 0.8. In green, we have the eBOSS galaxies, which go from the redshift 0.6 to 1.0. So if you took this plot on the top and you flipped it so you're looking along the Z-axis, what you'll see is a two-tiered effect. You would see this large footprint that combines the entire sample, where we have this redshift extent that goes roughly halfway. In the smaller but overlapping eBOSS footprint, we will have additional galaxies that will go from halfway up the redshift extent all the way to the entire redshift range of redshift 1.0. So if you're looking at this along the side, this will kind of look like a wedding cake tiered effect. On this figure, we also have the yellow points, which represent the voids that we have found in this survey. In the bottom, you can see the energy profiles for the CMAS footprint, the eBOSS only footprint, as well as the energy profile of the voids in these two regions. When we ran our void finding on this data, we found approximately 4,700 voids in the sample that passed all size cuts. The void finding is done using the revolver code, which is publicly available on GitHub. Look under Sesh's GitHub account. To correctly account for void finding in redshift-space, this code first uses an RST removal reconstruction technique to estimate the real space galaxy positions from which voids are then found. This is done as it's shown that void finding in redshift-space leads to selection biases in the sample. We can get around these selection biases by using this reconstruction technique. The reconstruction requires a grid of data values on which it is ran. So Revolver handles this by running reconstruction over this whole grid and void finding on these reconstructed positions. Once a void finding has been ran, we can take our void centers and correlate their positions with redshift-space galaxies in order to build a redshift-space void galaxy correlation function. We can also use the reconstructed galaxy positions and do a correlation of the void centers with these reconstructed galaxy positions in order to get an estimate of the real space cross-correlation function. Once we have these two data vectors from Revolver, we then also need to get density and velocity dispersion profiles. So in addition to redshift space and real space correlation functions described in the previous slide, estimates of density and velocity dispersions for the eBOSS sample are shown in the bottom figure here. The way that we found this is by taking a box from the Big MD simulation. From this simulation box, we created an eBOSS-like mock by taking the survey footprint and mapping that out into the simulation box. We then match the energy profile of the eBOSS survey in the Big MD box by downsampling again. Once we have this eBOSS-like mock taken from the Big MD simulation box, we can then run void finding and find our void positions. Once we have the void positions, we can then take these positions back into the simulation box, and we can look at the positions of dark matter particles and velocities of galaxies around these void positions in order to get our density profile and our velocity dispersion profile. So once we have these and we have our redshift space and real space correlation functions, we can put all this together into our fitting code. So our fitting code uses an MC technique to explore the parameter space. As our data vectors had a beta dependence from the RST removal step, we must account for this, and an MC exploration of the posterior is done. This is not trivial to do, and so we have released our fitting code under the name Victor, which is also available on GitHub. The GitHub page for Victor will have examples of the fits that we ran for this eBOSS analysis, as well as previous fits for similar work done on the CMAS sample. Results for the eBOSS DR16 data release are shown on the top here. On the left, we have the monopole. On the right, we have the quadrupole. Black points show the measured data vectors in a DR16 sample, and in blue, we have the best fit theoretical model. By eye, we can see that the theoretical model fits the data extremely well, and so we can make accurate estimations of the parameters. Parameter constraints from these fits are shown on the left, where you can see our best fit for F sigma 8 and the ratio of the alpha parameters from voids alone. As you can see, accurate measurements of both these parameters can be made using voids. On the right, we have a test of the systematics. To test the systematics, we use the approximate easy mocks that has come with the data, as well as full n-body n-series mocks. We run our analysis on each of these and use their known cosmology to test how well we were able to predict this fiducial cosmology. This is shown on the right, and systematic errors are a small contribution. This is less than 1% for the ratio of alpha perpendicular over alpha parallel, for example. So this is our results for the void-only measurements. And on the next slide, let's see how well this compares with eBOSS consensus results. So we can see how well these measurements compare with measurements from BAO and RSD. In blue, we see the consensus results for this technique. Orange, we see results from just voids, and in green, we have combined BAO, RSD, and voids to get the most accurate and most precise measurements that we can. So we can see that voids have a much higher precision in measuring the Alcock-Paczyński parameter, and the parameter constraints are mostly orthogonal to that from galaxy clustering. This means that there is a huge gain of information to be had by combining BAO, RSD, and voids together. And combining these techniques together will produce the most accurate parameter estimates possible from these galaxy surveys. The improvements from adding the void constraints can be shown here. We present our findings for DM over RD, DH over RD, and the growth rate. The improvements in errors for DM over RD is 23%, 28% for DH over RD, and 13% for the growth rate. This equates to reducing the allowed volume by 55%. This shows just how useful voids are getting further information out from these galaxy surveys. So just as a reminder, this is not using any extra data, this is just applying a new technique to the existing data, from which we are able to get results from voids that can then be combined with previous work to produce extremely accurate measurements. The results shown here are fully consistent with lambda CDM. So we have shown that there's a lot more information in galaxy surveys than can be extracted with just 2-point statistics. We've gone through the basics of our void analysis and shown how our new void measurements are a robust new method to extract more information from these galaxy surveys. Voids can add a lot of information on top of BAO and RSD results, and this technique should definitely be applied to all future galaxy surveys in order to get the most accurate constraints possible. That is everything from me. Thank you all very much for your time.